Welcome to this episode of Eureka, and we are going to have a very interesting conversation with the director of Central Glass and Ceramic Research Institute in Calcutta, Dr. K Muraleedharan. You might be wondering, what is this institute? This is one of the earliest scientific institute in the country and part of the CSIR family. Before we start the conversation, let's take a very quick look at his brief profile, and then we are going to have a very wonderful conversation. Keep watching Eureka.
Dr. K Muraleedharan is a man who wears many hats. He heads the CSIR Central Glass and Ceramic Research Institute, the only institute dedicated to research and development in advanced glass and ceramics in the country. In addition, he also handles the charge of Director, National Metallurgical Laboratory. Dr. Muraleedharan obtained B.Tech and PhD degrees from BHU IT Varanasi. Before coming to CSIR-CGCRI, he worked in various capacities in DRDO, providing advice and insights into material-related activities. Dr. Muraleedharan's research interests include the science and design of advanced material and multi-scale microstructural characterization, among others. Dr. Muraleedharan has received many awards and recognitions. Noted among them is the Eminent Engineering Personality Award by the Institute of Engineers in 2012 and the DRDO Agni Awards in 2005 and 2007.
Thank you for being with us. It's wonderful that you have been able to spare your time in midst of all your work, and also I think the imminent travel that you are going to have immediately after this show. Let me start with this question, which is the kind of question that I ask most of the people who come for this show. If I'm going to ask you, you have more than 30-40 years of research work in total. If I'm going to ask you, like, what are the three major papers or academic work that you have done, which you would bill as, something that you are even proud of? What would the three things that you would say?
Right. The very first experimental work I did, I am professionally an electron microscopist, and the very first work I did was with the quasi-crystals. The quasi-crystals in those days were just discovered, and it was something which exhibited a form of symmetry which otherwise is forbidden. Okay. And this work we did, and we showed, following a paper by the very famous Linus Pauling.
Linus Pauling, who got twice Nobel Prize.
He got Nobel Prize twice, once for chemistry and once for peace.
Okay.
And he was very old by then, but still he was very active. And he wrote an article in Nature which showed that all quasi-crystal story is nothing new. These kind of structures exhibited in the past also by aluminum hydride. And we showed two very direct derivatives of that structure. One of them showed quasi-crystalline nature, while the other did not.
Okay.
So one turned out to be an arrangement of atoms in a quasi-crystalline manner, which one would expect if these kind of orders existed in the liquid, and if the solid inherits it, it will solidify into a quasi-crystalline nature.
Okay.
And this was published in Nature, and for a scientist to have his first paper published in Nature,
that would have been a very wonderful
I was in heaven.
Yeah.
Okay. The second part of work is that we were working with materials for the gas turbine materials, and titanium based intermetallics was a very promising material, and people all over the world were adding aluminum to titanium.
This material is kind of people were thinking that something like aeroplane or other construction that may be best material, right?
Yeah, as I was trying to tell you, the material which is used in a gas turbine, it has to retain its strength property up to very high temperatures.
Yeah.
They were expecting titanium aluminates to have properties right up to 650 degrees centigrade,
okay,
which should have been ideal for a very high turbine entry temperature. So people are adding aluminum to make an intermetallic called Ti3Al, and this, however, did not exhibit enough room temperature ductility. Why is room temperature ductility required? Is because you need to work with this material. So if you have to work with the material, it should have adequate ductility, so that if you drop it by mistake also, it should not crack up. However, it had high temperature property. To bring in the room temperature ductility, we added niobium, another third alloying element, and that brought in a new phase called B2 at those days. And during my PhD work, I worked on the phase relations of this alloy.
Okay.
And I again could employ the latest techniques in transmission electron microscopy to unravel the internal structure of this material, and that is another very gratifying work. The third work I would quote is the work I have done with my students of late, which is in looking at the internal structure of electronic materials, like materials like gallium arsenide, gallium nitride, and these works are now had very large publications. We have had 3 PhDs, 2 from IIT Delhi, 1 from University of Hyderabad, and currently we are now making systems in this country where gallium nitride is grown, and these are going to be the future next generation electronic materials.
Basically, these are all materials which are going to make, let's say, the next generation electronic and computer material, which
Correct.
can make it even more compact and maybe more reliable, right?
Right. Gallium nitride will do 2 things for you. One is that it will make high speed electronics, switches and other things. The second, it will do that it will make blue-green lasers.
Okay.
And blue-green lasers are required for underwater communication. So these are materials for the future.
That's interesting. I mean, you have had 3 different areas which are, maybe 3 different part of your academic career. You have shifted from one to another.
None of them have any link to the work I do today, which is glass and ceramic. That's very interesting.
That's a very interesting thing. So you have been keeping yourself, let's say, fresh all through your academic career.
One could say that, right?
That's a very wonderful opportunity for somebody. Doing the same thing for 50 years, I suppose people will get bored, or maybe you won't be that productive later in your life. That's a very interesting point. Let me shift to the institute where you are now. I mean, you are heading this institute for about last 1 year, 1.5 years. You have come to this place new. And this is one of the oldest institute in the country which is working on glass, ceramic, and now I think modern areas like optical fiber, nanomaterials and things of that kind, right? So if somebody is going to ask you the similar question about your institute, like, okay, say some 3-4 major stuff it has done in its history which has contributed to the growth of this country, what would you say them?
Let's dwell a couple of minutes on the past history of the institute. As the Council of Scientific and Industrial Research was set up in this country, Glass and Ceramics Laboratory was one of the first laboratories thought of. And in fact, the foundation stone was laid in December 1944, before independence, and the laboratory's funds were sanctioned in the year 1945. However, due to the time it took, it came into being only in 1950. By then, 4 other laboratories have already come up. So we can say in kind of hierarchy, we are the 5th laboratory. And initially, the person who set up the laboratory, Dr. Atmaram, worked with our founder, Director General, and their job initially was to work for problems for the World War. And they were in Kolkata. So we had that intimate relationship with Dr. Atmaram, Dr. Shandiswarup Bhatnagar, right here in Kolkata. And Dr. Atmaram was the person who had developed large number of furnaces for the glass industry. And glass and ceramics are the industries which thrived in this part of the world. And the initial mandate of the laboratory was to provide equipment, technical expertise, as well as trained manpower to the glass and ceramics industry.
Which was a kind of a local industry thriving in those days.
That's right. But of late, it has moved away to other parts of the country. But our laboratory has not stopped supporting this industry. Today, we support the local industry. We also support the industry in Kurja in Naroda. Kurja for the traditional potteries and Naroda for the tile industry.
Before we move into those discussions, perhaps we will take a very short break and then we will continue this conversation. It's going to be very interesting. Keep watching Eureka. We are going to take a very short break. After the break, we are going to talk about something very, very interesting. One technological improvement made by this institute is saving close to about 2,100 crores of foreign exchange every year. Unbelievable, but it's true. We are going to discuss about it and more after the break. Keep watching Eureka. A short break. Welcome back to Eureka, and we are having a very wonderful conversation with Dr. K Muraleedharan, who is the Director of Central Glass and Ceramic Research Institute in Calcutta, which is a constituent unit of CSIR. Before the break, we were talking about some of your work, and then I was mentioning that you are kind of saving almost like 2,100 crore of foreign exchange to India every year. What is this magic?
All of us know the flooring tiles we use. All our drawing rooms, all our flats today have this, and they stay flat.
Yeah.
And to give this property of this tile being very flat, especially when you put it in a furnace, fire it and take it out, we had a constituent called the Ukrainian clay. Ukrainian clay, imported from Ukraine as the name suggests. And the Ukrainian clay was a necessary constituent which gave it the required property. Research done over the years at Outreach Center in Naroda, we have developed an equivalent Indian clay, which today completely has replaced the Ukrainian clay. And figures today indicates that we export 40% of our production in this country of these tiles. And there is no imported component today in that tile. We are given this free to all the industry manufacturers here in the country. And as a result, the savings estimated is around 2,100 crores per year, that too in foreign exchange. And this, I think, is a good achievement for the country. And probably many people don't know about it. So I'm glad you thought about it.
It's an important point to make, and particularly given the fact that maybe the overall budget of your institute will be less than 100 crore per year.
About 100 crores in a year, including pension and salaries.
Yeah, but then the kind of foreign exchange saving by one technology which has been made by this institute is about 2,100 crore per year, which is, I think, a very, very
That's right.
important point. And it also shows that it is important that the nation invest in science and technology. I think that's a very important point, I suppose this particular example shows. Right. Moving to aside, other than this, what are the major areas, let's say, this institute has done for the country?
The institute, we are also very aware of the problems of the people who are in the bottom of the pyramid. So we have few programs. One program is in the state of West Bengal, where the drinking water availability is very poor, especially because, as you may be aware, that there is arsenic and iron contamination. So based on the ceramic technology we have developed in this laboratory, which is in the form of filtration, a membrane filtration, we now have set up large number of units with the help of West Bengal government, and this makes potable water available to a large number of people here. We have also given this technology to 3 entrepreneurs.
Okay.
So it is also accessible to people here. West Bengal government has approved 2 technologies for arsenic removal. One of them is this, the other one is from IIT Madras.
Yeah.
So this has been a very successful project. Working on this further, we are now trying to make the ceramic membranes also cheaper. Okay. So that process is now we are trying to do with a major industry giant, which is H&R Johnson. And we are trying to make these membranes available at a lower cost in this country. And
it's also, I think, a very important story which many people would not know, that how in a very unseen way institutions like yours is touching their life, touching the life of poor people in this country. I mean, people who may not have otherwise access to good drinking water. That's an important point. I was also told that you are one of the major pioneers in optical cable.
Right. Yeah, optical fiber today is our major activity, and this is a flagship product of this laboratory. In fact, we were in optical fiber business right from our beginning. It is one of our early times. Dr. Meghnad Saha's son worked in our laboratory, and he, along with his colleagues, set up this tower, and we drew optical fiber in this country for many years.
Like how far away, I mean, how far back this would have been? Like this?
It would have started in the early 50s.
Early 50s, when people were not even majorly talking about.
That's right.
Yeah,
that's right.
That's a
but any technology takes time to mature, and we one day gave this technology to many people in this country. However, due to commercial reasons, they have bought technology from other places. But even today, I'm very proud to say that around 70% of the optical cable used in this country is still made in this country. Yeah. So that is due to the early effort of ours. But we have then moved on, and we said that our role is in making specialty fiber. So we make specialty fiber today in this laboratory, and it is used in 3 major applications. One application is where to make laser, fiber laser.
Okay.
The second application is to make fiber amplifiers. Okay. And the third one is what is called fiber Bragg gratings.
Okay.
And in all these three cases, we have now reached the industry stage. That means our technology has been now either transferred to an industry, or we are ready to transfer to an industry. We have pilot plans running in our institutes, which is demonstrating the use of these technologies. And also in one particular technology, which is the fiber Bragg gratings, we demonstrated this in a company called Stone India, who are the manufacturer of pantographs for the Indian Railways.
Yeah, pantograph are the thing which actually touches the electrical wire in an electrical engine, right? Electrical rail engine, which actually draws the power to the engine.
Right. The pantograph connects the engine to the overhead cable, and the pressure that the pantograph imparts on the cable can either break the pantograph or even the cable and snap it, and then you have a major disaster. Sometimes we lose one pantograph in the process. So what the laboratory has done is, using a technology called fiber Bragg gratings, we have now very precisely able to determine the contact force and the location at which the contact force is applied by the conductor or the pantograph on the conductor. And this will then allow us to either raise it or bring it down, so that the life of the pantograph can be saved. Indian Railway has come and seen this. Recently, the member of Niti Aayog, Dr. Saraswat, visited us, and we demonstrated this to him. We have a laboratory unit, and we will soon, in a year's time, we'll be putting this on a loco and we'll be demonstrating to the railways. And I think this has a potential to replace the current pantographs on all the locos in the Indian Railways.
That's an interesting point. I mean, maybe we need to take a very short break. Don't go away. Keep watching Eureka. We are going to have a very interesting conversation after this. Keep watching Eureka. We'll take a very short break. Welcome back to Eureka, and we are having a very wonderful conversation with Dr. K Muraleedharan, who is the Director of Central Glass and Ceramic Research Institute in Calcutta, a constituent unit of CSIR. Before the break, I mentioned that you have prepared some strategic material. You know, material which, technology which no other country would be willing to share with countries like India. Can you tell us something about them?
Right. We have been working with atomic energy, and one of the requirements of the atomic energy is to have if there is a hot cell inside which, say, nuclear reaction is going on, and you would like the operator to watch inside.
Okay.
But at the same time, he is not affected by the radiations which are coming out. So if you had gone to a hospital, you would have found there is some special lead glass they use. Yeah. We use a similar technology. The glass we make here contains up to around 70% lead oxide. Okay. And this glass we are not able to get from abroad for all our strategic purposes. So based on a requirement of atomic energy, we have set up full technology in this laboratory, which uses a platinum pot technology. What I mean by that is, the glass is melted in a platinum pot, and this is a very corrosive material, and also at the melting temperature it flows like water.
Okay.
And it's very corrosive. So we have set up special facilities in this laboratory, by which we can make actually big windows which are of 1 meter by 1 meter by 50 millimeter thickness, that means huge windows. And these windows, based on orders, based on our technology which we developed, we have supplied nearly 22 tons.
22 tons of this?
Of glass to the atomic energy, to various power plants. Okay.
So, which means that almost any atomic power plant we visit, there is an unseen hand of your institute.
Our glass will be there.
Yeah, yes, very interesting.
Yes.
Yeah.
You will also see another contribution of ours in the same atomic energy. The nuclear waste after the spent fuel, when it comes out, it has to be immediately trapped and kept away, so that people are not exposed to radioactivity. So we have set up a unit by which we make glass nodules, and these nodules are mixed along with the liquid waste that comes, and it gets entrapped and immobilized in the form of a glassy matrix. This can then be safely kept away in stainless steel containers and kept away, and it won't be affected by rainwater or storm water or whatever it is. So this whole technology also we have made, and we have transferred this technology to industry, and the industry now is supplying to the various requirements of the atomic power plants. And it is important to note, every time you change the fuel, you need to develop a new glass composition to hold it, and we have been constantly working on this. Again, we have supplied close to around 55 tons of this material to various atomic power plants.
Very interesting. We have been talking of your past, let's say in some sense your present, but I think your institute should also look at future, like for example, let's say 2020 or 2030,
Right.
you know, forward-looking technologies, new emerging areas. What's the kind of plan that you have as a director who has taken over this institute, let's say in the last 1 year, 1.5 years? What do you think the institute should move towards?
So, if I stick to glass and what we want to do in glass, in the area of glass, the next area we want to get into is we have made a small beginning there by making laser glass. There is a glass which will be used to make the laser beam itself. Okay. So, we would like to go and make lasers. We have made a beginning with CAT indoor, and we would like to now tomorrow move on to disc lasers. And the disc lasers are ones which will give huge amount of power, which can be used for purposes where you need high amount of energy in a short time. So, that is one direction we want to go. We also want to use our fiber optics capabilities, and we would like to develop up to 5 kilowatt fiber laser, which can again be used when you need large amount of power for a short time. We also want to make a difference in the optical communication, and if you look at today, the CAT TV segment today uses our erbium doped fiber amplifier. We would like to go and use this also for little higher wattage, because that is the requirement of the new cities coming up. Today we are looking at smart India and having a modern town, new towns, and for the new humanitarian settlements, we need to have faster communication. So, technologies like fiber to home, which is next to dish to home.
Okay.
So, the fiber to home technology, the heart of that is the fiber.
So, at some junction you may have to amplify the
Right.
optical signals that is coming.
That's right.
So, the kind of amplifier that you will build, I mean the boosters that you will build will actually give that enough.
Right. Our role is 3 because the fiber, the energy is bundled, the signals are bundled together and is sent to say apartment building or something. From the apartment building, then it goes to each apartment.
Yeah.
And at each apartment, you want to break it into, say, a TV signal.
Different systems.
A TV signal which only has to deliver one way.
Yeah.
It has to give you a picture or a voice. Telephony where you have to convey both ways, and then the data. Yeah. So it can be split into 3 different, and on all 3 we will have 3 different fiber amplifiers.
Okay.
So you will see a composite unit. The prototype of that we have already conceived, and in the next few years we will be able to give this to the Indian cities, and Amravati, which is going to be the new capital of Hyderabad, will most probably become our first customer.
Okay, so that's where you are going to first initially roll out and see actually how it works in the ground.
Yeah, we are talking to them.
Okay, that's a very interesting idea, and with this perhaps we need to end the conversation for lack of time. We could have talked a lot and quite a lot, but time is a constraint. We had a very, very wonderful and very, very interesting and very illuminating conversation with Dr. K Muraleedharan, who is the Director of Central Glass and Ceramic Research Institute in Calcutta. Keep watching Eureka. We'll come back with a conversation next week with another Indian scientist from an Indian lab. Thank you.